Welcome to our hydrogen startup showcase. We're very excited to have you all here. I wanted to start just by reminding us all why hydrogen's important, and I'm sure our amazing companies are also going to talk about this, right? But 90% of our primary energy use globally is in the form of fuels, and it is imperative that we continue to innovate on clean, low carbon, zero carbon, carbon neutral fuels. And hydrogen, is really one of the only solutions that exists today that is capable of being scaled. Could account for up to 10% of the mitigation we need in terms of reaching our climate goals. 12% of energy demand. Those are big numbers. So I know that there's this period of uncertainty around hydrogen, particularly in wake of announcements this week. But I want to remind everyone in this room that the world is clearly on a trajectory for using hydrogen. And certainly in my travels to Europe, Asia, the Middle East this year, I've seen nothing but extreme excitement and a lot of momentum around hydrogen. So we have 6 amazing companies that are going to tell you all about their work. We're going to go in alphabetical order, just so everyone understands the format. We're going to do 8 minutes per company of pitch, and then we're going to give 5 minutes to audience Q&A. So with that, it's my pleasure to introduce Karen Baert, who is the CEO of Ammobia. Karen, over to you.
Thank you, Naomi, and I'm really excited to be here alongside a few of my favorite fellow companies working in the hydrogen space. I'm going to talk about ammonia. Maybe let's start with a quick raise of hand. Who has heard of ammonia? All right, that's pretty good. So some of you might be thinking of this stinky product that you use to clean your bathroom. Well, I have good and bad news for you. The bad news is ammonia is stinky and it will always be stinky. The good news is, what if I tell you that ammonia could not just clean your bathroom, but it could mitigate up to 5% of global greenhouse gas emissions? And that's why we're here talking about ammonia today. So I'm Karen, co-founder and CEO at Ammobia. At Ammobia, we are revolutionizing ammonia production. Now, why does that matter? Today, ammonia is one of the most important molecules on Earth. It's the second most produced chemical, and it's mainly used as a fertilizer today. More than half of the world's food is dependent on ammonia as a fertilizer. That also comes with 2% of global greenhouse gas emissions. And the exciting thing with ammonia is that massive current use case as a fertilizer is just a start. The reason why in the energy world we care about ammonia is that on top of its use as a fertilizer, it's also a really attractive clean fuel. Because one, it's clean, there's no carbon in the molecule, it's NH3, so when you burn it, there's 0 CO2 emissions. 2, it's pretty easy and cheap to transport and store, especially if you compare it to other molecules like hydrogen. So that comes with a lot of new use cases for ammonia. One of the big ones that I want to point out here is ammonia as a maritime shipping fuel. That alone would double the size of the already very large ammonia market and enable us to tackle an additional 3% of global greenhouse gas emissions. But to do that, we need low-cost, low-carbon ammonia. And here's the challenge. Today, ammonia is high cost, high carbon. Ammonia is produced in these massive chemical complexes at extremely high pressures and temperatures, 200 bar, 500 degrees Celsius, and a relatively low conversion efficiency of just about 20%. Now that's where Ammobia comes in. At Ammobia, we enable low-cost, low-carbon ammonia production. We can produce ammonia at an order of magnitude lower pressure than the conventional process. So 20 bar instead of 200 bar, and also significantly lower temperatures, around 300 degrees Celsius instead of the traditional 500. We do all of that while increasing the efficiency from around 20% to 80%. And I'm excited to share that in our latest reactors, we've actually achieved a big breakthrough. Our long-term goal is 80%. We've already achieved a 67% efficiency or conversion efficiency, which is more than 3 times the conversion efficiency within traditional Haber Bosch. So with that, we're on a path to scale this technology and de-risk it as fast as possible. Over the last year, we've done a 1,000x scale-up of our tech from a reactor kind of the size of this clicker to a reactor my size. And now we're doing another big scale-up every year to get our pilot up and running at the end of this year and have a first commercial system up in the field in 2027. I mean, the ammonia market is a massive market. If you just capture 10% of the market, you get to a very impressive revenue growth. But the better news is that we already have the customers lined up to achieve that revenue growth. So we're negotiating our first offtake agreements for next year, and then we have 5 conditional contracts for customers who want to buy our first commercial units. Now, if you want to go fast, go alone. If you want to go far, go together. We're extremely proud of the great set of supporters, investors that are working with us today. We've been able to raise over $9 million of funding, a good split 50-50 between VC dollars and non-dilutive funding. This is our team, a great set of experienced engineers and experts with decades of experience in the clean molecules world. I'll leave it at that for an introduction, and I look forward to your questions. Thank you. Great question. The first unit will be a 10-ton-a-day system, which is kind of like small-scale ammonia production. First customers will be a mix between a few US projects. These ones are projects in the US Midwest, where today ammonia is really expensive because it's far from the current production in the Gulf Coast. And the second kind of group of projects are in Europe, because there's a lot of interest in distributed low-carbon ammonia production there as well.
And your production use case, will you primarily be using or producing fuel or fuel and fertilizer, or will you see the market?
Great question. We think that as an early-stage company with a new technology, you shouldn't take market risk and technology risk at the same time. That's why we're starting to produce ammonia for the current ammonia market. So agricultural use cases and industrial use cases, they use ammonia today, but pay way too much because they're really far from the current production. From there, of course, as we de-risk the technology, we will also move to the new use cases, including shipping fuel.
Very nice talk. Thanks a lot. Can you elaborate a little bit on your technology? So why do you need low pressures and low temperatures?
Absolutely. Great question. So it's an innovation to the thermochemical Haber Bosch process. We use the same catalyst, but we add a new material to the reactor that is a separation material. Think about it as an ammonia selective sponge. What that material does is, as soon as there's ammonia produced or ammonia in the gas phase, it takes ammonia out of the gas phase, kind of through that separation or sorption. And as a result, you keep producing ammonia. It's basically an equilibrium reaction. When you take the reaction product out, the reaction keeps going. So that's the principle on which our innovation is based. That's why we can produce at a much higher efficiency. That's also why we can produce at much lower temperatures and pressures. So it's sorption-enhanced reaction.
So it seems like a slam dunk when it comes to commercialization. There's an existing market. And I assume you're producing at a lower cost. So, as you said, so what are the challenges in terms of ramping up your,
Yeah, it's a great question. We are at a really important and exciting time where we have most of the science risk behind us. So to your point now, it's really about execution, engineering, and scaling up. The most important thing for us, I would point out 2 things. One is having the right talent to scale this up effectively. We're leveraging a lot of the current expertise in the oil and gas world, in the thermochemical world. Second one is having the right partners who are willing to build some of these first systems with us.
questions for Karen?
If you have a sorption process in the reactor, do you need more reactor footprint or volume per unit of ammonia produced?
Great question. So because there's a new material, you could indeed think we need a bigger reactor, but at the same time, we have a higher efficiency or higher conversion for the same amount of catalyst. So the two equal each other out. So we expect to need around the same footprint or reactor volume as the traditional process. Good question. The biggest one is actually now we're limited by the size of the reactor. So our current models already estimate that as soon as we make the reactor longer, we'll already get to the 80%. So it's reactor size, but it's also continuing to optimize what materials we're using exactly and how we integrate them into the reactor. So material optimization. All right.
Wow, Karen.
Thanks, everyone.
You always set the bar so high. Thank you. Next up, Maggie, you're going to help me with the deck here, right? It's my pleasure to introduce Anthony Koo from Clear Skies Hydrogen.
All right, good afternoon. My name is Anthony. I'm a co-founder of Clear Skies Hydrogen. We're a pre-seed startup looking to make affordable, scalable hydrogen vehicle refueling solutions. It's our view that hydrogen will play an important role in the decarbonization and electrification of mobility, particularly in heavy-duty and commercial fleets, where challenges that you see in all battery solutions related to grid build-out and competition for electrons will create a space for a hybrid fleet. So the key points then, if I can move this forward, are shown here. So the problem is competitive economics. Zero-emission transportation, especially in this current policy regime, needs to be cost competitive as one of the primary drivers. The market, we believe, exists today. In transit and trucking, there are commitments in California for 1,000 vehicles, and there's an immediate need for fueling. So the market may not be as big and as exciting as people thought it was a few years ago, but it is here, and there's an immediate urgent pull. Our solution really goes after the current cost drivers in existing hydrogen fueling station designs and drives those down to allow you to unlock a path towards diesel parity cost, which we think is really what you need to revitalize this market. In terms of attraction, we've got a commitment. We've actually got market pull and an agreement with a major trucking OEM to basically fuel their trucks over a multi-month pilot within the next 12 months. And the goal of that is to generate a data set in terms of reliability that will allow transit agencies and other people that need to deploy these units to be able to see the reliability they want to be able to sign commercial deals. We have an LOI listed here. We're on the verge of getting an MOU and more binding agreements in the very near future. Our team, my co-founder and I, both come from 20-year careers in industry, bringing technology from lab into the market. We've also worked in hydrogen refueling previously. Most recently in 2020, we delivered innovations specifically into this space. And the offering, we plan to open up a seed round in the summer to generate the capital to be able to move forward with the pilot demo and then getting into the market in 2026. So that's my overall story. What I'd like to do then is spend a few minutes just to unpack those points. So let me start with why hydrogen. I think this audience is probably already convinced of that, but I think it's important to recognize that despite advances in battery chemistry and technology and megawatt charging, you still really run into infrastructure problems when you try to scale batteries. So it's things like power outages, the risk of being able to build out grid interconnects in the right amount of time, competing demand from data centers. Those are things that really are giving pause. There are a lot of people working on innovation in that space, but those are hurdles that need to be overcome if you want to envision an all battery electric heavy duty fleet. Hydrogen, though, has different scaling characteristics, and so it's our view that you can have a very complementary blend of electric and hydrogen. The problem, though, is that hydrogen stations today are too expensive and very inflexible, and so that's the problem that we're trying to solve. So our solution you can see here by comparison. So on the left side, you see a picture of the largest commercial hydrogen fueling station in the US today. It's at the Port of Oakland. The footprint is about 3 times the size of this room. And so if you look at the equipment there, about 40% of that equipment or less is actually used to put fuel into the vehicle. The rest of it is used actually to capture venting losses and boil-off losses that occur along the way. So you don't really need that, except for the fact that if you don't have it there, you end up losing so much hydrogen that the economics look even worse than they might be with today's technology. So what we're trying to do ultimately is to simplify that technology. So if you think about the boil-off driving those things, you can see the costs at the Port of Oakland were at retail stations $36 a kilogram, which is 4 times what you need to be in the diesel parity competitive space. So what we want to do is go after those root causes of boil-off, and I'll show you how we're going to do that in a moment. If you can get rid of those, you can eliminate 60% of that station. You can simplify the station, which drives down your CapEx and your OpEx, and then you're on your way down that cost curve, and you have the potential to really improve the economics and change that. And so along the way, you get not only the economics, but you get the efficiency, you get reliability because you have less equipment, and you also get scalability because you have a smaller station that can start off with small fleets and then grow into it rather than overbuilding a station on day one and paying these penalties where, you know, your station is designed for 200 vehicles, but if you're fueling, let's say 30, you end up basically carrying all that CapEx and fixed costs over too few units of fuel, so you pay a double penalty on that. So our view is you can actually step your way down. So let me show you how we intend to do that. So this is the technology that really unlocks everything. It's a 3D printed pump, which I actually have here. This is a single printed piece. It's 50 pounds or so, and we'll have that at our table if you want to come by and check it out. But really the inspiration behind this comes from my co-founder who's worked 30 years in hydrogen, including 10 years working with cryogenic systems. So he understands the limitations of existing pumps. And by using 3D printing as a technology for manufacturing, which is not something you could do 10 years ago, we've now introduced features into the system and the design that specifically go after the thermal and the fluid mechanics aspects that are driving boil-off at the level of the pump operation. So this looks like it's basically, this is a thermos that we've been able to print a single piece here inside our vacuum chambers as an example of some of the innovations that we've deployed here to begin to work on these issues of boil-off. So when you stack all of the different innovations that we're looking to put in, we're looking to reduce the boil-off by 90%. And when you roll that up to the level of the station, you can save not just at the level of the pump, but you're also saving at the station design with the equipment that you eliminate, and you're able to get these other numbers of 50% reduction in CapEx and OpEx. Since my co-founder and I both come from industry careers, we understand the value of intellectual property, so we have a deliberate plan to protect the property, including 6 patent applications to build a boat, as well as trade secrets around design and operation, which you don't want to patent because those are the secret sauce that really allow you to be differentiated and maintain long-term capability. So when you roll all of that up, what you end up with are mobile refiller modules. And so what you're looking at here is an artist depiction of a 20 by 10 foot container. That's the station in a box. So it's a much smaller footprint. It's containerized, so if you've got a transit agency that's starting off with an ultimate fleet of, say, 100 buses, but they only have 10 buses on day one, you can begin to start with a starter kit and then grow into that over time rather than having to overbuild your station entirely. And so this modularity gives you flexibility not just at an individual site, but if you're now thinking about a refueling network, you have the ability to work through in a much more capital efficient manner. And then the table that you see on the right is just some indicative numbers just to give you a sense of the capital cost advantage. So rather than spending $25 million on a station, you can cut that down to under $10 million. That's our initial estimate of the cost advantage. So in terms of progress then, we've been at this for a bit of time with some early investment from Breakthrough Energy and Mercator Partners. We spent 12 months developing design and a full-scale prototype, including work here. This took us about 8 iterations to get the printing correct. We are now in the field working through validation. So we expect to have first hydrogen fills within the next couple weeks. And then on the back of that, we're working with the vehicle OEM that I mentioned at the beginning of the presentation to work out the details for a truck filling demo. And so that truck filling demo would be something that we're filling trucks every day, every night, for several weeks. And the idea there is to get the performance data over an extended period of time, so then you can have a transit agency or a drayage fleet or a local operator have that confidence that this is something that can actually work reliably. And that's what you need to be able to unlock the market, which is what we're trying to do in 2026. So it's a super aggressive schedule. It's not one that I think is particularly sane, but it is one that we're trying to move forward with. So that's our story. Happy to answer questions and happy to if you want to come by and lift the dumbbell here, happy to have you do that as well. So thank you for your attention and happy to answer any questions. Yes.
I think it's a general perception that 3D printing as a manufacturing technology is more expensive than more based solutions. Do you see any significant reduction potential with the process that you're
So the short answer is yes. So this thing looks like it's heavy and it's solid, but it's about half the size of the next smallest pump. There are other pumps that exist that are about the size of me. Like actually 7 feet tall is one of the ones that's out there. So that's one thing, is just you able to shrink the size of the material. The second thing is because we're building in vacuum chambers, this is a single printed component that took about 48 hours to print. If you were to make this traditionally, what you'd end up with probably 30 components, something much more expensive, a lot of welds, and your thermal insulation wouldn't be anywhere near as good. So there are niche cases where you can go through and use the specific capabilities in a way that's intelligent. So that's something that we've done. The other thing that we're doing is piggybacking off of the metal 3D printing ecosystem that's really developed over the past 10 years. So it's really oil and gas and aviation that are looking to print stainless steels, Inconels, a variety of materials with incredibly tight tolerances. So they've sort of underwritten the entire development of contract manufacturers that can do these things. So as I said, we couldn't do this 10 years ago, but it's something right now that we feel like is competitive.
And your market is primarily for diesel.
So in this case, we think hydrogen, the first place to come in is heavy duty, just because from a competitive point of view, that's where you might struggle with scaling battery electric fleets. You can pursue other things where you're looking to put hydrogen into mobility applications. But for us, that beachhead market is one where we feel the immediate pull. And that's actually driving why we're so aggressive in the schedule, is that coming to the market, the people that we're talking to are asking for better solutions. And so that's why we're trying to really match up and sync up the schedule. Absolutely.
System.
Right.
What conditions does the hydrogen need to be that
Yep.
then goes into
Yep.
the system?
Yeah, so in this case, we are a liquid hydrogen pump. So liquid hydrogen shows up at the station. So the station in a box doesn't have the cryo tank. So if you actually look at the picture on the right, you see the container, and then behind it, there's a cryo tank. So you do have to pay for that. The other piece, that you do get rid of a lot of the other equipment there. And so coming in is liquid hydrogen. Going out, you can actually have compressed gas of a variety of different types. So from technical terms, you'd have H70, H35. So 700 bar, 350 bars compressed gas. You can also deliver from the same piece of kit, cryocompressed. So there's another company that's thinking about cryocompressed. There are people looking at liquid on board, and so our system could be able to do that, but I wouldn't push it there just because the technology value proposition doesn't make sense. So you can buy a single kit that can serve all of the major modes right now that are out there. Yeah, absolutely. Yeah, absolutely. So that's a great point. Is when you think about the value chain, right? You have to stack all those different components. So right now, if you're taking delivered liquid hydrogen, Plug Power, for example, has a spot market where it's generally $8 to $9 per kilogram of liquid hydrogen delivered to your site. So then on top of that, you subtract that out, the rest is what you're paying for the station to operate. And the station itself might be designed to be much better, but if it's got boil-off losses, that's just money going up your stack. If you've got low utilization, that's basically a penalty that you're paying. So those can be fixed, but it's one where you can work that problem. If you actually look at that, right, if Plug Power is offering you, let's say $9 to $10 per kilogram, you're already above diesel parity, so there's a problem. You can think about, as you begin to scale up, you can do direct contracts with industrial gas companies, and you can start to negotiate that down. And you can also activate growth of the market over time to begin to get scaling effects to squeeze the entire cost stack. Okay. Thank you.
All right, next up we have Henry Moise, who is the co-founder at Hydrify. Over to you.
Okay. Hi, everyone. Really excited to be here. My name is Henry Moise, and I'm a co-founder of Hydrify. Natural hydrogen, in my opinion, is going to be one of the greatest energy opportunities of our generation. And one of the biggest challenges with it right now is accurately identifying these resource rocks, and that's what Hydrify wants to work on. So let's start with some introductions. Yashi, she's the real rock star of the team. She's the one who developed the algorithm that drives our approach. She also brings a strong background from oil and gas. Yelchin, current GSB student, also with a background in consulting, and he's going to really make sure that we have the strongest business case moving forward. My background is in chemical engineering, mostly hydrogen production from natural gas, until I met Yashi and she convinced me to work on something different. And then Dr. Stephen Graham, ex-dean of the School Earth and Energy and Environmental Sciences. Long list of accolades wouldn't fit on this slide, so we'll just leave it at that. So why geologic hydrogen, or what is geologic hydrogen? Quick show of hands, who in here has heard of geologic hydrogen? right? Good amount of people. It's pretty popular. So geologic hydrogen, there's a few different ideas about where it comes from. One of the commonly held ideas is that you have water in the subsurface and it reacts with iron-rich rocks and it produces a hydrogen-rich gas. Regardless of how it's produced, what we do know is that current projections of how much is produced annually, if we could tap just 1% of that, 1% of that would give us about 200 years of abundant, low-cost, on-demand hydrogen. And that's really exciting. Focusing on probably the most important metric, which is the cost aspect, low cost, we currently have a TEA, which is, it's actually public, it's online, everyone can go see it. It's the culmination of over 150 interviews with hydrogen producers, customers, natural gas well operators, a lot of people. And the big takeaway that we found from it was, two big takeaways. One, natural hydrogen can be produced for about $0.50 a kilogram, stimulated, which would be the injection of water into these resource rocks to produce it, would be about double that, $1 per kilogram. The second one is, of course, this doesn't include transport. The main thing that we want to show with this is that transport obviously is very important, and we want to be able to co-locate these sources next to off-takers. But the biggest opportunity I see from this, or we see from this, is that theoretically it's cost competitive without incentives or co-product utilization, like other companies will have to rely on. Yeah, so let's talk about some of the people who work in this space. There's a lot of companies in the space right now. A lot of them are doing great work. The challenge, however, is that most of them will rely on historic well data, so legacy well data. One company, for instance, Hytera, doing some really exciting stuff in this field. They recently had a press release a few weeks ago. They measured 96% at one of their well sites. It's very exciting, but not that surprising since they're drilling next to a well which already had measured these high hydrogen concentrations. And that's not to bash what they're doing. I think what they're doing is great. It's really just to drive home this message that we don't really know how to find these sites once we've run out of these legacy wells to drill near. And that's what Hydrify wants to work on. So once we run out of these sites, we'll have to resort to wildcatting, which will have very low success rates. And if we use natural gas as a proxy system, you can assume about 5 to 10% success rate when you're actually going out trying to find these sites. So when you incorporate this, you can spend about $20 to $40 million just for a single viable well when you're doing natural hydrogen. Hydrify, of course, wants to reduce these numbers, and we think we can get it down to about an order of magnitude less, about $2 to $4 million per well. And we want to use this using our algorithm, which currently, in its current state, can achieve about 50% success rate. And we'll talk about in a little bit, actually this summer, we hope to refine this number even more. So the algorithm that we use is a culmination of Yashi's PhD work. It takes in geologic data, geophysical data, mostly public data for the time being, but right now we have some field data that's gone into this, and this summer actually will bring in a bit more. We, of course, overlay this with a demand map so we know where the off-takers are and where to find these sites such that we reduce these transportation costs tremendously. So this summer, we've actually been able to fundraise enough to bring on an intern and actually go out to several of these pilot locations that the algorithm has spit out. And we hope to verify this, and hopefully in about 3 months, we'll have some exciting news for you guys. So where are we right now? Right now, we're a very early stage company. We're still at the identification phase. We want to verify the presence of hydrogen based on the algorithm's outputs. This summer, we'll be able to do that, hopefully. And once we're able to find enough of these sites, we hope to lease the land or buy the mineral rights and start to fundraise for a test drill. Assuming we find the high hydrogen purities that we want, we'll of course play to our strength, and we'll partner with oil and gas companies, hydrogen off-takers, and move from there, because the ideal scenario, obviously, is to sell hydrogen at low cost and abundance. So we're very interested in partnerships, and with that, I'll leave it up to questions, and thank you for your attention.
I have a question. What is an economically viable hydrogen well? What does that look like?
Yeah, let's go back a little bit. Yeah, economically viable well. So that means it's producing at $1 per kilogram or less when we do that. So we looked at several parameters. Of course, it's a TEA, so it's only as accurate as the inputs you put in. But we base it off of success rate, percent of serpentization that you can achieve, distance traveled. So we see it as $1 per kilogram or less would be an economically viable well.
Other questions
plan to like lease a land like without like informing any of the big like oil and gas majors like this is where natural hydrogen is? Because they would have the capacity to then just like lease the land and take over it and
Right. So right now we're taking advantage of the fact that although oil and gas companies are aware of this, they're not all that interested in it at the moment. So we're gonna look for federal lands, BLM lands, and the idea is that if we find these lands, we'll be able to lease them before we release any news about what we find there. Would be the main idea. Yes.
Okay, so I guess most hydrogen that is used today is from, is the right word electrolytic hydrogen?
Reforming hydrogen.
Yeah, okay, sorry. What's the delta in price? Because you were saying $1 per kilogram, so what are you beating out?
Right, so depending where you are, reforming hydrogen can be anywhere from $1 to $1.50. So when we say we're doing it for about half of that, of course, that's assuming that we're not having to transport it off. That's a big thing. So they bring in natural gas and they use it on site. So it's probably the key differentiator there. But just for the production at the well, 99+% purity hydrogen, we can do it for about $1 or half $1 per kilogram.
And no CO2.
No CO2. Or very low CO2. I think it's comparable to electrolysis. There was an LCA done here at Stanford, and they found it's about comparable with electrolysis.
So you're this small to sell this software, or are you going to become a project developer? The initial role is just to test your software's capabilities.
Right, so we plan on using this software to find the locations, and we want to develop the locations ourselves. So we see this as a tool to help us identify the best locations for this.
Other questions?
Last question, most likely. So what is your algorithm doing? Is taking satellite image, then you go to every site and collect any chemical sample, or how do you do that?
Yeah, so this would be a great question for Yashi. So right now we are relying on mostly public data, geophysical and geologic. But when we go out this summer to do the pilot test, we'll be doing field gas samples, so gas soil samples, and that will feed back into the algorithm with our own proprietary data. So right now, mostly public.
Thank you.
Any more for any more? Thank you,
Great.
Henry. That was great.
Thank you.
All right, next up, Caleb Boyd, co-founder at Molten Industries.
My name's Caleb Boyd. I'm the CTO and co-founder of Molten Industries. It's great to see a lot of familiar faces in this room, and some people I haven't met. Anthony, Breakthrough Energy Fellow, a fellow Breakthrough Energy Fellow we haven't met till today. So a little quick thing before I get started of, why we're here and a little bit about our founding story is my co-founder, Kevin Bush, and I were PhDs at Stanford, material science. We spent a lot of late nights in the McCullough building and the Moore building, if you guys are familiar, over at the engineering quad. Came to a lot of events like this, mostly for the free food. And yeah, saw a lot of really interesting startup talks and gained a little bit of knowledge, and then started tinkering and building furnaces to split methane or natural gas into hydrogen and graphite in a garage on Stanford campus, up by the dish, actually. A really nice professor who we were renting out a room from let us plug into his EV charger and then wrap up a little home-wound furnace, heat up methane to about 1,000 Celsius, and then split it into hydrogen and graphite. And that's how we got started. So it's nice to be back on campus and back to where we are. And so this presentation is going to be, I know this is a hydrogen-focused thing, but it's going to be talking a lot about graphite, and that's basically because somewhat accidentally we discovered a way to make really high-quality graphite using this process. And so hydrogen is somewhat of a byproduct for what we do. Why should you care about that? Well, that means that we can, in our belief, sell the lowest cost, cleanest hydrogen on the market, which really ties into what we founded the company for, which is to decarbonize the heavy industrial sector. And then, yeah, we call ourselves a purple company, and that has two main things. Naomi touched on the kind of state of affairs in the world right now, or in the United States government specifically. But you can see us as making critical materials from natural gas that's primarily dominated by China. Or you can see us as a clean hydrogen and decarbonization company. And similarly, you can see us as a hydrogen company for things like heavy trucking, or battery company for heavy trucking. So we split the middle either way. Anyways, I'm going to start talking about lithium-ion batteries. So lithium-ion batteries, 25% graphite by mass. China currently dominates the global graphite supply for that, and they're restricting exports. There's two ways you can get graphite today. You can either mine it out of the ground, and then you need to use really nasty acids to leach out the rock, create a very high purity concentrate, and that goes into a battery electrode in which you stuff lithium ions into. Or you can take petroleum needle coke and synthetic graphite, heat it up to about 3,000 Celsius, half the temperature of the sun, for around 3 weeks, turn it into graphite, so graphitize those carbon bonds, and put that into a battery. Both of those processes are almost entirely done in China today. And what we're doing at Molten is a third way to make battery-grade graphite using methane or natural gas. So what we do is we take natural gas or renewable natural gas, we pump it into a proprietary reactor. That's kind of the secret sauce that we developed in the garage. And then it splits. We heat it up electrically, so using electrical resistive heating, very similar to a toaster. And then it splits into graphite and hydrogen. The hydrogen fluidizes out the graphite continuously, and we separate it out in a simple cyclone process, and then can use the graphite flakes for downstream processing and producing battery anodes. And then we can send on the clean hydrogen to companies that are looking to put it into trucking or sustainable aviation fuel, or to make clean steel with it, or renewable diesel or things like that. Our flake graphite, this is what comes out of our reactor on the right there. Looks exactly like commercial graphite. That's what comes out of our reactor. You can see the really nice hexagonal shapes. We've put this into batteries. It delivers very high quality results in batteries. We're sampling this right now with major battery customers. And yeah, this is kind of the story and journey of where we've gone over the last several years. So this is a picture of Kevin and I in the garage at Stanford campus, just near the dish there. We spent about a year in that garage tinkering around, getting the chemistry right. And then we built out our first pilot in Oakland, California. That's where our headquarters is now. Using Breakthrough Energy Fellows funding. We were also backed initially by Union Square Ventures in 50 years, two amazing funds. And then since then, last year, we raised a Series A funding round from Breakthrough Energy Ventures. And we're currently using that to scale up to a modular commercial scale. So that's the photo you see on the very right. That black container module produces 1 ton of hydrogen and 3 tons of graphite a day. We're currently commissioning that unit now, and then looking to site a full-scale commercial plant, which would be 20 of those commercial modular units. Yeah, can't say how much we really are thankful for all the employees that have made this a possibility today. We work with an amazing team. Everyone is engineers and technicians. These guys are incredible. The amount of stuff that they are able to build in a short period of time is fantastic. And so I really want to thank the team and highlight that. We've also got an amazing advisory board. People from the Stanford ecosystem, Arun and Jane specifically, are, I'm sure many of you guys know them, just huge supporters to almost every company that I know of that's come out of this ecosystem. Has really benefited from their support. And then, yeah, the investors and funding that we've talked about has been incredibly useful as well. This is where we're looking to go. So I mentioned that gigafactory. We call it a gigafactory because 20 of those modular units produce enough for 10 gigawatt hours of batteries per year. And so that's what we're looking to site right now, start construction mid to late 2026, and have the commissioning in late 2027, early 2028. So thank you, and I'll open it up for questions. Yes. Almost certainly not. Oh, this gigafactory. Yeah, almost certainly not. If we could get $36 per kilogram of hydrogen, then maybe. I don't know anyone who's willing to pay $36 per kilogram of hydrogen for 8,000 tons of hydrogen a year. But we're currently looking in places like Houston, Texas, Louisiana, the Gulf Coast. We're evaluating several sites in places like Kentucky, Illinois, and Ohio as well. Yeah, thanks.
On the current scale, what is the cost of hydrogen that we're seeing without including the selling price of graphite?
Yeah, so at this scale, this modular production plant right now in Oakland, it's really expensive. We pay something like $15 per million BTU of natural gas, and at peak, we're paying around 50 cents a kilowatt hour of electricity. Stuff is expensive in Oakland. So the hydrogen here is very expensive. At this first gigafactory, we're looking to sell that hydrogen between $1 to $1.50 per kilogram. And then at full scale, we think we can get to below $1 per kilogram. When you look at, so we talked earlier about hydrogen today, comes mainly from natural gas through steam methane reforming, costs around $1 a kilogram. That's not necessarily counting depreciated capex. So with depreciated plants, you can potentially get lower than $1 a kilogram. If you start to look at actually replacing natural gas, so if you're replacing natural gas, for example, in a DRI shaft furnace to make clean steel, you need about 70 cents a kilogram to be economical with existing DRI shaft furnaces. And if you're looking to replace natural gas on just like a per million BTU basis, so like just straight heating natural gas going into a burner, you need about 50 cents a kilogram hydrogen cost. So those are the prices that we would love to target in the long term. But yeah, that's difficult to do.
What's the carbon intensity of the hydrogen at the end of the process?
Yeah, good question. It depends on how you count it. So the primary source of emissions in our process is upstream methane emissions. So if we're using clean electricity, our process itself generates no CO2 emissions. Natural gas has upstream methane leaks, so that's the primary source of emissions in our process. If you push all those emissions to the hydrogen, then you're looking at it's around 1 to 1.5 kilograms of CO2 per kilogram of hydrogen if you're using 100% renewable electricity. The interesting thing is that if you look at, like, for example, the 45V tax credit, which may or may not exist shortly, the graphite flakes that we produce are much lower carbon intensity than the way that graphite's made today. And that's primarily because you're doing either strip mining or you're doing this process at 3,000 Celsius, which has a ton of NOx and SOx and methane emissions as well. And you actually get a credit for that. So from the 45V tax credit standpoint, the way it's written today, we're actually eligible for the $3 per kilogram credit because of that co-product allocation. Yeah. As it's written right now in the reconciliation bill, 45V would still exist if we just start this facility construction in 2025. So you can either look at that as a bad thing, or maybe we just need to raise funding sooner and start facility construction sooner. But yeah.
Are there any entities that could be off-takers for both for you, hydrogen as well as the graphite, that you would, because like natural gas pipelines are everywhere, so like, why not move it around?
Yeah, that's a good question. Some entities have been interested in that, like steel companies use graphite for anodes for electric arc furnaces. They would also be interested in using hydrogen. The graphite that we make, which is this powder basically, these flakes, has not been shown to be, it would be like a research project to put it into steel electrodes. Most battery companies don't use large quantities of hydrogen. So we've been seeing this as being a two different end customer process. If we're making electricity, then we could supply electricity to those battery companies with the hydrogen. It's just a low value use case for the hydrogen, but yeah. Anyone else?
So in the color spectrum of hydrogen,
Yeah. Technically, it's turquoise hydrogen. It's basically blue. It's basically blue hydrogen. I mean, you can think about it as like we're taking a fossil, instead of having to dump CO2 into the ground, we sequester that as graphite. So most people don't burn their batteries intentionally, so the graphite is sequestered most of the time.
Colors are terrible anyway.
The colors are terrible anyway. Yeah, unless you make it with, if we make it with nuclear, then it's some, I don't know what pink plus turquoise would be, but whatever that color is.
1 kilogram of CO2 for every kilogram of hydrogen, is that
Yeah.
what you said? That is 90% lower than
Yep.
the standard. So,
SMR,
yeah,
gray hydrogen.
that's what we
Yep.
should focus on.
Yep.
Great. Any other questions? Well, this was
Great,
great.
thanks.
Yeah, thank you.
So next up we have Joe Sawa with Membravo.
Right, great. So my name is Joe Sawa. I'm the co-founder and CEO of Membravo. And we live in a world today, our society is demanding more industrial output, including more energy and more hydrogen. And yet we want that at lower cost and lower carbon intensity. At the same time, chemical separations alone are the source of a tremendous amount of energy and product waste in the industry. So 15% of global energy and emissions goes to just taking mixtures of molecules and separating them. It's remarkable. Hundreds of billions of dollars of product that we just made go to waste because they can't be separated from the stuff that they're mixed with due to ineffective separation technologies. So I'll give you an example with this nice little cartoon. So tens of billions of dollars of hydrogen go to waste every year because existing technologies are not durable enough to separate that hydrogen from high temperature, harsh gas mixtures that exist in the industry. Therefore, companies have no choice but to burn that gas. This has been taking place for decades, and there's not much to do about it. But we solve this problem by simply recovering hydrogen out of those waste mixtures, allowing that value to be brought back into the asset, reducing emissions and reducing cost. And now we actually work in a variety of different applications across industries. Today, we're gonna talk mostly about hydrogen. So our membranes work like filters. They allow hydrogen to pass through and they block other gases. And unlike existing hydrogen separation technologies, ours is designed and field tested specifically to work in the most extreme industrial environments. Our product also works for our customers because it's easily retrofittable into existing assets, and it's profitable for them to use. So there's no need for subsidies or incentives. Again, my name is Joe Sawa. I'm the co-founder and CEO of Membravo. I spent more than a decade at Shell working in oil and gas and hydrogen, and I started Membravo to help decarbonize industries exactly like those. My co-founder Malad Yavari is a PhD in membrane technology, and he led the development of our technology at SRI, and we joined forces to bring this technology to market very quickly and very effectively. So we just got started. We launched the company in January 2025 when we spun out from SRI. We have manufacturing and headquarters in Menlo Park. To date, we've raised $250,000, and we've joined a couple exciting accelerators, Third Derivative and Plug and Play. We just heard, just yesterday actually, that we've been accepted to an amazing program, amazing accelerator. I can't share what that is yet, but stay tuned. Stay tuned for that. More than $10 million of U.S. Department of Energy funding went into the development of our technology at SRI, which, by the way, used to be called Stanford Research Institute, right down the street in Menlo Park, where they perfected the manufacturing process for this technology, and they also field tested the technology at third-party locations, including the National Carbon Capture Center, where our membrane separated hydrogen from high-temperature syngas, which is a really challenging industrial separation, and it's also how 99% of hydrogen is made today. The technology is patented, and there are additional trade secrets and confidential know-how that ensure that the tech can't be reverse engineered. So like I said, our membranes are exceptionally robust, which means that they work in applications where other technologies don't. We can capture value, we can reduce waste in these new applications. Typically, we see, coming out of R&D, that researchers are looking for materials and membranes that have high permeance and selectivity, but then they have to prove that the materials are strong and manufacturable. Then they have to make sure that they're compact and cost-effective, and sometimes those materials get commercialized, and that's what we see in industry today. But they're really lacking the top part, which is the heat tolerance and the chemical tolerance, which means that their applicability in all the variety of industries where hydrogen separation is needed is very limited. There's just a lot of applications that can't be served. There's a lot of unaddressed need with this technology. Again, if we sort of scan the landscape between pressure swing adsorption, these are competitive technologies. Pressure swing adsorption is the incumbent technology. There are other polymer membranes as well as palladium membranes and cryogenic distillation, but it's really the combination of the cost effectiveness, the resilience to impurities and temperature, and the ability just to get the job done, to do the separation that's needed between hydrogen and other gases. We're critically positioned to serve lots of these unserved markets because of the shortcomings in the existing technologies and the strengths of ours. So our membranes add value in really a wide range of applications. Those are in industry today, in refineries, chemical plants, and DRI steel mills especially. $200 billion worth of hydrogen is used every year today, and tens of billions go to waste. We're also looking at the exciting emerging applications that we're hearing about today, where there's new ways of producing, consuming, transporting, and storing hydrogen. Many of them can be made more efficient through better separation. So that's blue hydrogen, methane pyrolysis, natural hydrogen, ammonia cracking, renewable diesel production, sustainable aviation fuel production. It's really a long list. Virtually everywhere, again, that hydrogen is produced, consumed, stored, or transported, we're finding value from these membranes. Just a quick example. So gray hydrogen or blue hydrogen is made from steam methane reforming today. It's separated via technology called pressure swing adsorption, but about 20% of hydrogen goes to waste just due to the ineffective nature of that separation technology. By retrofitting our membranes onto that unit, we can simply capture hydrogen that's coming out of that waste stream, recycle it back into the process, and thereby increase production of that process by 20% with no change to the inputs, no change to the fossil fuel inputs. So that's an improvement in efficiency, reduction of carbon emissions, and obviously a big boost to the economics for that project or for that asset. Okay, so briefly, looking beyond hydrogen, we do serve other markets that have to deal with high temperatures and harsh chemical mixtures. And in fact, our first customer, we shipped product and received revenue from our first customer a couple months after spinning out in the semiconductor industry. So that's a liquid separation that we're currently piloting. But really, hydrogen has been sort of the largest interest that we've gathered thus far. Lots of other applications to explore as we go forward as well in parallel. So we're here down at the bottom. We're doing small-scale pilots with our first paying customer. Through the rest of 2025, we'll be scaling up our product to build larger modules. Going into the end of 2025, start of 2026, we'll begin pilot testing with our first customer. After that pilot test is complete, we expect commercial purchase orders, and then our challenge becomes scaling up to meet the demand that we've generated. So we're currently raising a $2 million pre-seed round to prepare for and start to execute those pilot projects. That means hiring our core team and engineering that commercial scale product. And we're extremely confident in our technology, our product, and our business overall, even in this sort of environment, in this landscape, because we have strong unit economics today that work in any policy scenario, and we have a very short path to profitability and to scale up. So thank you very much. Would love to connect and take your questions.
Manufacturing process novel, or is it like similar to what's already being done in other industries? Like how you unique the membrane?
Yeah, it's certainly novel. We make a hollow fiber membrane. The process is novel to create this novel material, which has unique properties that work in the industry. So there are some similarities. It's kind of analogous to existing manufacturing processes, but the specific recipe is quite unique and patented and quite novel.
Scaling up the manufacturing.
Yeah, correct. The overall archetype of the manufacturing process is very well known, and therefore we can work with contract manufacturers, we can partner, or we could scale up ourselves because that equipment is available. Sure, yeah, go ahead.
So in terms of, membrane durability has been like the long-standing issue, I think, for this type of separation in general. So when you say, resistant, what kind of lifetime are we talking about? Like if you were to put it on a steam methane reforming unit, how long would you expect your membrane to
Longer than the competitors. So the answer, it really depends on how intense the environment is that we're putting it into. But we know that it survives at much higher temperatures. So we're also intending to put these in environments where no membrane has gone before. That's really what we want to hit first, and then come back and compete in the existing spaces on durability. So the fact that we can operate, we operated in the field up to 1,000 hours was the field test that we've done thus far. At about 180 degrees C, we test in the lab at 225 Celsius. Competitors, our very best competitor can go less than 100. Many go to 80 or 60 or 40. So that range, we have just a very bizarrely robust polymer. We need more run hours to determine the end of life. Thus far with our field test, we have a straight line when it comes to performance. So no degradation, which is amazing because that's what we want to see. We want the product to survive forever. But we don't have a curve to extrapolate to figure out what the end of life is. That'll come with more pilot testing and long-term operations.
Other questions for Joe?
Yeah, go ahead.
What's the
the commercial planned product in terms of, like, I guess, gas throughput, any unit you want to? Sure, yeah, so our kind of minimum commercial scale that we're talking about here, we're calling that, nominally it's 200 kilograms per day capacity, and that would be about 3 feet long, 4 inches in diameter. There's no reason we can't go bigger than that in the future, but that's kind of what we're calling minimum. We can manufacture at that scale and build more units and just put them in parallel to get more throughput just based on the customer system. And long term, we can always make that bigger and get more throughput as well. Sure.
Could you replace the pressure swing absorption like unit altogether and just have this?
Yeah, so it depends on the process. We envision a few different scenarios. In some cases, we can replace PSA. In many cases, like I showed here, we actually work really well as a hybrid system. So a PSA today is achieving really high purity, meeting the customer's requirements fairly well, but with low recovery. So again, you know, this 20% losses is incredible, incredibly high. But by making a hybrid system, PSA plus membranes, we can keep that high purity, but also boost that recovery to something much more reasonable. In some cases, we could replace it entirely, but the hybrid system makes sense a lot of times. And that's great for us because there are many, many units that need retrofits. We don't have to tear out the old unit and put in a new unit. We can just complement what's already there. Sure.
Quick, how does your pricing compare to your competitors?
Yeah, so we are in the same price range as existing competitors that have less durable technology. So we're in the same ballpark, you know, nothing out of the ordinary for customers, but they can use this product in places where they can't use other technologies. Yep.
I'm curious if this has good application for like electrolysis and wet hydrogen, like separating gas and liquid, or is it really mostly for gas separation?
We are seeing a little bit less traction in that space, to be totally honest.
It's already solved.
Sort of solved, and the deoxy units are there to remove trace impurities. It seems like the industry is like fairly happy with some of the solutions that are there, and so I'll never say never, but we're not looking there first. All right, thank you so much.
It's my privilege to introduce Suhani Mohan, co-founder of Nazadia.
Thank you for all the patience. Now we know how to extract hydrogen geologically, make graphite out of steam methane reforming. We'll address another important part of the entire value chain of hydrogen, which is hydrogen storage. We are developing solid state storage solution using metal hydrides. So coming to the fact that when a very important factor in terms of hydrogen ecosystem is storage, which is ignored. And we know that if we are able to decarbonize hydrogen production, there's a 500 million metric ton impact of CO2 reductions. So coming to the fact on why storage is critical. Apart from the fact that hydrogen can be produced in different locations, when we specifically look at green hydrogen production, which is hydrogen through electrolysis, there are certain hours in the day when it is more cost effective to produce versus others when the sun is blowing and the sun is shining and the wind is blowing. So for the remaining hours, there's a need for buffer and storing hydrogen. Secondly, hydrogen storage, we talked a little bit about off-gassing early on, as well as there's also perception of storing hydrogen in a compressed form, and there is a lot of permitting delays because of that. So safety is an important factor. And lastly, it is expensive. In many cases, hydrogen storage is as expensive or even more expensive than the cost of production itself, in the range of like $3 to $5 per kg, which is ridiculous. And when you look at the overall cost of either green or low carbon hydrogen productions, many of these projects become unviable. We started early last year through a Stanford Climate Ventures class. I am Suhani, I'm a second year MBA student, and we realized after speaking to almost 200 people in the industry that there are two different types of storage needs. One is buffer and backup. Just providing a very quick context, when you look at battery-based storage for electrons, you look at long duration storage and there's a different chemistry, and then there is short duration storage, and that's the same with hydrogen. On a daily basis, you need buffering if you're using green hydrogen production, and you also need backup in case your production unit is not working for a few days. There's a power, similar to power backups, where you need infrequent charging and discharging of hydrogen solutions. So that's why we looked at various different solutions and came across metal hydrides, which has been a technology that has been researched for almost 20 years by the Department of Energy, and billions of dollars have been spent in research, and a lot of good material has come out of it. Incidentally, my mother had also worked on this technology like 10 years ago and had commercialized this plant in India. But having said that, why did this technology not scale, and why do we only see compressor or cryogenic storage so far, is the fact that a lot of people were trying to use this technology for mobility and transportation application. And by logic, metals are heavy and they add to the weight and reduce the efficiency overall. So despite being significantly safer because hydrogen is stored at room temperature, almost like room temperature and pressure, the OPEX is really low. It's almost like a hydride gets formed and you don't need to maintain anything. It can stay like that for long durations, and has probably one of the best gravimetric storage capacity. You can store 2x more than liquid hydrogen as well. There were visible gaps. Also, the most viable metal hydride solutions, which are titanium-based, are very high capex. And there were few questions that come across in the industry about kinetics as well as durability. So when we looked at the solution, there were a lot of very good check marks, but a lot of issues as well. And that's where our innovation comes in at Nasadia. We have looked at combining two different alloys together, the two concepts of buffer and backup that I talked about. So there are two separate types of alloys that we're using. One is a titanium-based, which is expensive but has the best kinetics. So this is for your daily buffering. And then a magnesium-based, which is low cost, reduces your overall system capex significantly. But that's only triggered when you need huge quantities of hydrogen out. By doing this, we have effectively reduced the overall weight. We have reduced the capex, which becomes a big challenge in terms of new installations, as well as kinetics and durability. When we compare it to other types of storage solutions, there are many solutions, but either they are geographically limited, like salt caverns, which are probably the cheapest but not available everywhere. Then there's liquid storage solutions, which we talked about a lot. There are new ways of storage of hydrogen as different chemicals like ammonia or LOHCs. But metal hydrides using dual alloys is probably one of the best solutions when you look at stationary storage and not moving the metal around. Now the big question arises how big the market is, and that's the big question, that is green hydrogen really going to take off or not? But we see that there are two separate markets broadly to categorize the need of hydrogen. One that we talk about where hydrogen is competing with electrons for power backup, data centers, and replacing diesel generators. So that's one segment, but there's a very huge segment where hydrogen is used as a feedstock in ammonia, in methanol, SAF, and specialty chemicals, and also in steel and cement industries. That is where there is a lot more stationary storage requirement, and we are, at least from our beachhead market perspective, capturing some of those segments. We did one analysis from a TA perspective, looking at how does the cost compare with the incumbent, which is compressors, which most people are used to using. And there's almost like a 15% lower LCOS on the overall levelized basis, as well as the capex was 40% cheaper than compressors. This is because of the engineering on combining two different types of alloys, and we are able to bring the cost down significantly because magnesium is really cheap. In terms of how do we want to scale this, this is a capex solution. We would, just like selling batteries, these are solutions that we'll sell to industries, and eventually also look at system integration. And we can do it on both ends. One is hydrogen producers, either green hydrogen or different forms of low carbon hydrogen production methods. And then there's a consumer. And there are people in between who are project developers. Right now, we are seeing a lot more interest coming in from project developers because it's on top of their mind on how will they solve for storage, but we see integration coming in from both sides as well. Lastly, I think from our team, Chaitanya was a master's student. He graduated last year from Stanford and has looked at green hydrogen as well as storage for the over last 5 years. I'm doing my MBA at Stanford, and prior to this, I was a hardware entrepreneur working in a different industry, but also scaled it to 13 different countries. So I have like real experience and pain of building hardware technologies and also appreciation of doing that. Naomi is here, who has been a mentor from the beginning, and Dr. Mark Allendorf is the guy who has worked in metal hydrides over the 20 years at DOE, who is also our advisor. In terms of the stage, we are fairly early. We started last year as a student team, raised almost 100K over the last 1 year to develop our prototype, which is right now being developed in India. Over the next few months, once we have results of our lab-based testing of the dual alloy system and how we are optimizing the system, we intend to raise about a 2.5 million seed round. That's it. Thank you, everyone. I think from the largest market perspective, it is ammonia, but what we have seen is easiest to get into our smaller scale chemical manufacturing companies that require hydrogen. So it's not as competitive and nobody's targeting them, so we are going after them.
Is there a minimum size you need for it to be economic? Because I can see like you actually might not be competitive at the small scale because the capital cost is too high. You do have the weight, but that means more foundation and other costs. So like, what's the smallest tank?
So we are looking at a 10 kg system, which is also modular and replicable. That is something that can go in like the refueling station application as well. But at an ammonia plant scale, we are looking at a one ton hydrogen storage system, which fits into a 40 feet container broadly.
I think you noted about $3 as cost per storage of kilogram. Would be great to understand that, I guess, in terms of energy. And then also, I think you said at some point you could utilize waste heat. Is that part of the calculation for $3 or was it additional savings?
Yeah, so the heat transfer is not included in the $3 cost. So if you recycle the heat, it is supposed to go down further. At the same time, this is just an estimate, does not include economies of scale. This is what prices we got at this scale. I don't have the numbers on a kilowatt basis immediately, but I can get back to you. I have it somewhere. So yeah.
What's the activation temperature? Like how much, at what temperature does the hydrogen actually get released from the hydride?
You need to activate the metal hydride once, which is 400 degrees Celsius, but after that, the charging and discharging cycle happens at about 35 to 40 degrees Celsius. So it's not a lot.
So kind of like when you have batteries that are trying to do, say, power and energy at the same time, you're trying to do something similar, right? I would think the key about that is the controls, which I didn't hear you talk anything about,
Yeah.
which is going to be the key in like getting continuous flow, getting processes going. So like what, are you looking at that? What's your approach to that?
I think this is a great question. We are slightly early. We were focusing more on the material science aspect so far in terms of choosing the right alloys, which offer the best kinetics and thermodynamics. But I think the next big phase for us is the control system integration. And a lot of, I think it is good for us that a lot of work has happened in the battery ecosystem to kind of optimize that. And that will be an important next step for us as well.
Have you identified applications that are willing to pay $3 a kilogram for hydrogen?
Right now, I think it was in your slide that it's almost like $18, or people are paying ridiculous amounts already. So $3 seems reasonable, but at scale, it has to be around $1.50 per kg is what is the estimate that we are getting at.
I think for transit buses, $3 is actually economically legal.
Yeah. Yeah.
Like Molten with using methane, carbon, graphite, is there any sort of use for your output of titanium or magnesium?
I didn't understand the question, sorry.
Are you using in titanium or magnesium? Are you using that in any sort of way after the use of hydrogen?
I think it's It's a continuous process that keeps getting recycled. I'm not sure if I got your question right, but are you asking about recycling the material? Yeah, so there is a little bit of powderization that happens, but you can actually take it back to a furnace, heat it, and activate it again and recycle it.
Great.
Thank you.
All right, thank you. Well, please join me in giving all of our awesome speakers and companies a big round of applause. Thank you.